Kelpine, an 8th grade science teacher at Carl Middle School and an OERB master teacher. Today's lesson, Physics Fun with Newton, is brought to you by the people of Oklahoma Oil and Natural Gas. Let's get started. Have you ever wondered why things move the way they do? Like why your body moves forward when someone slams on the brakes, or why it's harder to push a full shopping cart versus an empty one, or why a rocket goes up. Today we will explore Newton's laws of motion to try to answer these and other questions you may have about the world around you. Feel free to pause this video at any time and come back when you're ready to move on. Have you ever been riding in a car and the driver has to slam on the brakes? Did your body suddenly move forward? Why does this happen? The answer is relatively simple. It's inertia. Let's take a closer look. For our first investigation, you'll need a few metal washers or a few coins like pennies, a smooth, flat surface, and a piece of paper to record your results. First, stack all but one of your washers or coins. Aim the extra one at the bottom of the stack. Sketch this setup on your paper and predict what you expect to happen when you push the extra washer or coin toward the bottom of the stack. Now, give the coin or washer a good flick or push. It may take a couple of times to get it just right. Take time to record your results on your paper. You just experienced Newton's first law, often called the law of inertia. Part of Newton's first law of motion states an object at rest stays at rest unless acted on by an unbalanced force. Vocab. Inertia is the tendency of an object to resist a change in motion. All matter has inertia. Recall from our sound thinking lesson, a force is a push or pull. Unbalanced force just means that the force is enough to make an object change its motion. And balanced forces happen when the total forces on an object are zero, resulting in no change in motion. Before anything happened, the forces were balanced and there was no change in motion. When you pushed the metal washer or coin at the stack wanted to stay where it was because of inertia. But the washer or coin you pushed had enough force, an unbalanced force, to move the bottom one out of the way. Let's watch that again in slow motion. Let's apply this idea to you slamming forward in a car when someone hits the brakes. The other part of Newton's first law of motion states an object in motion stays in motion with the same speed and in the same direction unless acted on by an unbalanced force. You're cruising along in the car and someone pulls out in front of you. The driver slams on the brakes. Your body continues moving in the same direction and at the same speed it was moving before the vehicle stopped. Lucky for you, you remembered to wear your seatbelt and it keeps you safe by pulling you back to the seat. Your body has inertia and it wants to keep moving forward, but your seatbelt essentially makes you part of the car. Some of you may have been on a school bus that took a quick corner or stopped suddenly. Same idea. Or if you've seen a magician pull a tablecloth out from under a glass, it's inertia. Can you think of other examples of Newton's first law of motion? Have you ever gone grocery shopping and noticed that it became more challenging to push or turn your cart as you loaded it up with groceries? Newton's second law of motion can help explain this and some other experiences you may have had. Newton's second law of motion relates force, mass, and acceleration of an object. In mathematical terms, F equals ma. Force is equal to mass times acceleration. When your cart is empty, it has a little mass, so it doesn't need a lot of force to make it accelerate. Vocab. Mass is a measure of the amount of matter in an object. Acceleration is a change in velocity. Velocity is the speed of an object in a given direction. For our second investigation, you'll need 2 toy cars or trucks. Identical cars or trucks work best. Or 2 ping pong balls and 2 golf balls. A sturdy piece of cardboard or wood. A book could work too. Some pennies or washers. A piece of paper and some tape to attach the pennies or washers and to make a finish line. Let's set up. First, lay your piece of cardboard, wood, or a book flat on a table or the floor. About a hand length from the end of your ramp, put down a piece of tape to mark your finish line. Tape your pennies or washers together in a stack. Place both cars or the ping pong balls at the top of your ramp. Slowly lift your ramp. They should cross the finish line at the same time. It may take a few tries. Once you've mastered your release, it's time to change the mass of one of the objects. With some tape, attach 10 to 15 pennies to one of your cars or 3 or 4 washers. Or trade a ping pong ball for a golf ball. I'm using the washers. Be careful not to tape your wheels. That way it can still go. On a piece of paper, sketch the setup and predict what will happen when you release the objects with different masses. Once you've made your prediction, it's time to test. Slowly lift your book. Record your results. Repeat your test 2 more times and record those results too. What did you notice? Did the mass of the object make a difference in its acceleration? Try investigating again with more coins attached to your car or with a heavier ball. What happens when the mass is even more? Can you explain why it happened? Newton's second law of motion explains that an object with more mass accelerates less than an object with less mass when the same force is applied. The force here is the pull of gravity. Another way to think of this relationship is if something has more mass, you have to apply more force to make it accelerate more. So your car that had more mass didn't accelerate as much as the car that had a smaller mass. Let's apply this to the shopping cart. An empty cart has less mass and takes less force to accelerate. The full cart has more mass and takes more force to accelerate the same amount. Here, the amount of force needed to accelerate the cart increases when the mass increases. You could consider trying to throw a basketball versus a bowling ball. Seems like a no-brainer. The bowling ball has a lot more mass than a basketball and would take a lot of force to throw it like you would a basketball. Can you think of other situations where the relationship between mass, force, and acceleration can be observed? Now that we've explored the first 2 laws of motion, let's take a look at that third law. Watching a rocket launch is a pretty incredible sight. Have you ever wondered how a rocket is able to lift off at the end of that countdown? Let's investigate. You'll need a balloon, some string, dental floss or sewing thread would work, tape, a straw, scissors, and a place to attach the ends of your string, 2 chairs or 2 walls that are close together. First, cut your straw in half. Then thread the string through the straw. Attach the ends of your string to stationary objects, 2 chairs, 2 walls that are close by, or 2 tables. Here I'm using my kitchen stools. Place a piece of tape over the top of the straw and make sure there's enough tape hanging over the sides to attach your balloon. Now blow up your balloon, but don't tie off the end. Tape it to the straw and move it to one end of the string. Now before we let go, predict what you think will happen when you let go of your balloon. Okay, scientists, we're go to launch in 3, 2, 1, blast off! Cool. My rocket zoomed forward along the string and even hit the stool and bounced back. Did yours do the same? Why did it do that? Newton's third law of motion can explain. The third law states, for every action, there is an equal and opposite reaction. The action here is the air from the balloon pushing on the air around the opening of the balloon. The reaction is the air around the opening pushing back. The balloon is pushed forward by this opposite force called thrust. Not convinced that air is pushing on air? I have some spring scales here, an instrument that can be used to measure force in newtons. As you see here, when one spring scale pushes on the second, the forces are equal. They both read 3 newtons. The one on the right is pushing on the left one with 3 newtons of force. And at the exact same time, the left one is pushing on the right one with the same amount of force. We call these force pairs because the action and reaction forces are always together. Let's relate this third law to a rocket blasting off. When the exhaust pushes out of the rocket, it pushes on the ground, action. At the same time, the ground is pushing back on the exhaust, reaction, causing the rocket to move, just like with our balloon. If you've ever bounced a ball, you've experienced Newton's third law. When the ball hits the floor, action, the floor pushes back on the ball, reaction, causing it to rebound or bounce back up. Ever been swimming? Yeah, that's explained by Newton's third law too. Your arms and legs push on the water, action, and the water pushes you back with an equal amount of force, reaction, and you move through the water. Can you think of other activities that show Newton's third law of motion? Today, we've explored Newton's 3 laws of motion. We hit the first law, the law of inertia, seeing that an object at rest stays at rest and an object in motion stays in motion, unless acted on by an unbalanced force. Then we raced through Newton's second law, F equals ma, which demonstrates the relationship between force, mass, and acceleration. More massive objects take more force to accelerate. And finally, we blasted off with the third law of motion. Every action has an equal and opposite reaction. In any interaction, forces act in pairs. Here's a challenge to try at home. Newton's Carnival Challenge. Most carnival-type games use Newton's laws of motion to bring fun and entertainment to our lives. Your challenge is to design and create your own at-home carnival-style game using materials from around your home and that demonstrates at least one of Newton's laws of motion. Once you've created your carnival game, take pictures or a short video of you or someone in your home playing your game. Email teachers@oerb.com and tag us on Facebook or Instagram @OERBOK, and you could win a prize. Well, scientists, I hope you've had some physics fun with Newton and me today, and hopefully you'll be able to explain more about the world around you.